So we have an understanding of the special theory of relativity, and we understand that the universe is Lorentz invariant, and we're now in the position that Albert Einstein finds himself in 1905, 1906. He has produced the special theory, and he now is trying to understand how to write relativistic physics, and he runs into the problem that gravity is not, as we understand it, a good relativistic theory. And we can understand what's wrong with it. Look at what the familiar form of Newton's gravitational force law, and everything about it is wrong. For example, there's a denominator there, r squared. Who's measuring r? Remember, if someone is moving, they would measure a different distance because of Lorentz contraction. Whose r do you use? Worse than that, when do you measure this distance? If I take the sun at this point, and I somehow manage to move it 2 astronomical units to the left, what happens to the force on Earth? Does Earth immediately respond? Because when do you measure this r? Earth is not allowed to immediately respond because Earth is not allowed to know about the fact that the sun has moved until enough time, 7 minutes or whatever it is, has passed for light to have arrived from the sun to the Earth, because no information is allowed to be transferred faster than the speed of light. Now, we know a resolution of this. Maxwell's equations, how do they do it? Remember, Maxwell's equations essentially start with Coulomb's force law between charges, remarkably similar to Newton's force law between masses. And we know how this is resolved in Maxwell's theory. The way it's resolved in Maxwell's theory is if you take a proton and an electron, and you move the proton suddenly, the electron does not respond instantaneously because the electric field where the electron is has not changed. The motion of the proton generates an accelerating charge, generates an electromagnetic wave. That wave is a ripple in the field that changes it from the value associated to the first position to the value associated to the final position, and when this ripple gets to the electron, then the electron responds, and everything is nice and relativistic and Lorentz invariant. So perhaps we can take Maxwell's equations, apply them to gravity, and have a relativistic version of gravity, and this is indeed Einstein's first choice. The problem is a subtle one. What we need is a field theory. We need something that will carry at the speed of light the information from one place to the other. Einstein's aware of this. He attempts to use Maxwell's equations, but he immediately knows that that will not work. The difference between this equation and this equation is an important one. The quantity appearing here is the electric charge. The electric charge is a conserved quantity, and Maxwell's equations imply, in fact, charge conservation, whereas the object appearing here is mass, and in Einstein's theory, mass is not conserved. Okay, well, modify things. What is conserved instead of mass? What is conserved is energy momentum. But energy momentum is a completely different beast than electric charge. Electric charge, remember, is Lorentz invariant. Every inertial observer measures the same amount of electric charge in a given region in space. On the other hand, mass or energy momentum is not Lorentz invariant. Different observers measure different energies and different momenta related, like T and X, by Lorentz transformations. This complicates the theory significantly. There's also a philosophical question that actually turns out to be very important for the answer, which is, what is a gravitational force? So how do you measure a gravitational force? Well, let's start. How do you measure the electric force? I want to measure the electric field at this point in space at this time. Well, I bring along something charged and I measure the force on it, divide the force by the charge. The answer is the electric field. You say, no, but perhaps you were mistaken. Perhaps what you were measuring was just the gravitational force on this object. I say, okay, I'll bring another object with the same mass as the first, but with the opposite charge. Now the gravitational force will be in the same direction, the electric force in the opposite direction. I'll look at the difference between the two, and the change is the electric. The one that changed between the positive and the negative particle, that's the electric force. Good. So now do the same for the gravitational force. So you bring along some object, you measure the force that gravity applies to it, you divide that by its mass, you get the gravitational acceleration. Very good. Now bring another object upon which... Oh, wait. There is no object upon which gravity acts in the opposite direction. There's not even an object upon which gravity does not act that you can bring and replace it with. In fact, all objects fall with the same acceleration. There's the universality that suggests that thinking of gravity as a force is kind of difficult because you can't even really operationally define how to measure it. Thinking along these lines, Einstein is working through it, and in 1907, he has what he considers, and in writing, his happiest thought ever, and his happiest thought basically involved jumping off the roof. If you jump off the roof, he realizes, there is no gravity until you hit the ground. The idea that Einstein is discovering and discovering the importance of, is the principle of equivalence. We made a big deal a few weeks ago about the fact that when you are in free fall, there is no gravity, and I emphasize that this is not some random idea. In space, everything is in free fall. Stars, galaxies, planets, they're all in gravitational free fall, so they're not experiencing any gravitational force. The converse is in fact also true. I can play with the apparent gravitational force by accelerating, making measurements in an accelerating frame, not in an inertial frame. Being an observer who is accelerating. For example, we've all had this experience. You get in an elevator, the elevator starts going up. As the elevator starts going up, you feel as though your weight had increased. Why does your weight increase? Because now the elevator floor has not only to hold you up against the pull of Earth's gravity, but also to supply the extra force to accelerate you up. And so the floor is pushing on you harder. That's the experience of weighing more precisely. And so the gravitational acceleration at a given point, at any given time, depends on your acceleration. And by picking a suitable acceleration, i.e. letting go of everything and falling down, I can make the gravitational acceleration relative to me at any point in space and time be zero. How do I do that? Just let go. And when I free fall, I don't experience gravity. The gravitational acceleration I then measure when I drop something, like when I jumped off that chair. When I was jumping and I dropped the ball, I measured a gravitational acceleration of exactly zero. So Einstein realizes this, and then maybe the whole idea of gravity needs to be abolished. You don't need to think of gravity. You just need to understand that we're working in an accelerating frame. So everywhere, the surface of the Earth should be thought of as accelerating up. I mean, of course, not getting anywhere, but accelerating up and relative to some inertial frame, which is in free fall. And because the floor is accelerating up, that's why we experience weight. This would work well were it not for the tricky fact that Earth is a sphere. You can't accelerate the entire surface of Earth up. You can accelerate it out. But if it did accelerate out, then it would not only be pushing us up, but also we'd be accelerating away from each other. We know how that happens. That has to do with tidal forces. What makes gravity gravity, what distinguishes gravity from just the result of measuring in an accelerating frame, what the actual gravitational force lies in is in those tidal forces of which I made a big deal a couple of weeks ago. The fact that the acceleration of gravity is not the same everywhere in space and time, that is what the result of the fact that there is actually a gravitating body called Earth. If the gravitational acceleration were equal everywhere, then you're actually in an accelerating elevator. Get out of the elevator and you'll measure a gravitational acceleration of zero. So this idea proves to be key in Einstein's solution of the problem of finding a relativistic theory of gravity. But right at the top, we can use it to good effect. So let's learn one important thing about gravity that will serve us well. So here's a cartoon version of the principle of equivalence. Here we have a spaceship. It's out in space. There's no gravity. It's in the middle of nowhere in space. It's accelerating up at an acceleration that I choose to call g. And what that means is that if you sit here and throw a little rubber ball, well, the rubber ball, of course, there's no gravity, there's nothing touching it. It will proceed to move in a straight line at a constant speed across space. However, because the spaceship is accelerating up, relative to the spaceship, the ball is not accelerating, it's moving in a straight line. Relative to the spaceship, the ball will appear to be accelerating down with acceleration g, because the ball is not accelerating, the spaceship is. Of course, bring that same situation over to the right-hand side. Here I have the same spaceship. It's sitting on the ground, it's not going anywhere, but there's a gravitational force, a gravitational acceleration of g as there is on Earth. And if I throw a little rubber ball, well, then it'll fall on the ground with acceleration g. From the point of view of looking inside the spaceship, you cannot tell the difference between being on the ground and experiencing a gravitational acceleration or being in the middle of nowhere and accelerating up. Good, so that's the principle of equivalence. We know about that. How do we do something useful with it? Well, here's what Einstein says. Imagine putting a little blue light bulb at the tail end of our spaceship and let this little blue light bulb emit a pulse of light, a little short wavelength pulse of blue light. Now, when the pulse is emitted, the spaceship is moving maybe with some velocity v. What v is completely irrelevant. I can always pick an observer that is moving at a speed v, and then for him, the initial speed of the spaceship is zero. And were the spaceship moving at a constant speed indeed, then this pulse of light would travel at exactly the speed of light relative to the spaceship, up to the top of the spaceship, and if I put a detector at the top to absorb it, I would observe that there was no Doppler shift, because detector and emitter are moving at zero relative velocity. Light moves at the speed of light anyway, there would be zero redshift. However, in this case, the spaceship is accelerating. If the height of the spaceship is denoted by h, then it takes a time of the order of h divided by the speed of light for this pulse of light to climb to the top of the spaceship. If the spaceship is accelerating with acceleration g, the change in its speed during this time while the photon is moving up the spaceship is of the order of its acceleration times that time. And so when the photon is absorbed, the spaceship is no longer moving at speed v, it's moving faster. The result will be, of course, that you can imagine v to be 0 by picking an appropriate frame. You have something emitted. The receiver is not moving at the same speed as the emitter. The receiver is moving faster by this amount, and we can use our understanding of the Doppler formula to compute the degree by which the photon will be reddened, because the receiver is receding from the observer at this relative speed, and so dividing v by c, we find this is the non-relativistic expression for the Doppler shift. We're working with small h, and so in that approximation, we can use the non-relativistic version. We're not going to be doing anything super relativistic here. What's good about this is that now the principle of equivalence tells me that the exact same thing happens on the right. If I put on the bottom floor of a building, or at the bottom of the spaceship sitting on the ground, a blue flashlight, and it makes a blue wave, that wave, when absorbed at the top floor of the building, will be redshifted. And what this means is that any light is affected by gravity. It has to be because of the principle of equivalence and what we understand about special relativity. And as you shine a light from the bottom floor to the top floor, the light is reddened. Of course, the reddening is not significant. GH over C squared is not a large fraction unless your building is exorbitantly tall. But if you make a precision measurement, you can do it. And this is not just about light, remember, because right here is an atom that is oscillating, or whatever, a clock that is oscillating with some characteristic period, as observed by someone at the top of the building. Clocks on the bottom floor run slow. The redshift, remember, is accompanied, just as it was in the relativistic redshift case. It just reflects the change in the way clocks work. So if you observe from the top floor a clock on the bottom floor, you will see that the clock runs slow. If you want to live a very long time, go live near the Dead Sea. You will age slower, albeit by a very small factor. Is this for real? Yes, this is definitely for real. And in fact, it was measured in a beautiful experimental tour de force by Pound and Rebka in 1959 in this tower over here on the left-hand side of this building, the Jefferson Lab at Harvard University. The tower was designed initially to do some magnetism measurements. In the 19th century, Pound and Rebka repurposed it. They put their emitter down on the bottom floor of this tower and their receiver at the top floor of the tower. And over this height, they found a very minuscule but completely consistent with Einstein's argument redshift. And then when they, of course, conversely, when they emitted light at the top, it was blue shifted by the time it reached the bottom floor. Everything is symmetric in that regard, but they needed, the redshift was minuscule. They used a technique called misspower spectroscopy to measure the wavelength of light with exquisite precision. These days, this gravitational redshift is all over the place. The little GPS receiver in your cell phone knows about the gravitational redshift, so it can translate the time of travel of the signals that it gets from various GPS satellites to their distance in a correct way, taking into account that the receiver is here on the ground and the satellites are up in space.